Oh, I think I don't have control now. Someone has to click on. Test 1, 2, 3. Ah, okay. So I have to keep it very close. Yeah. I think you just need to click on the slides, focus PowerPoint. There we go. All right. Thank you. Okay. So, you know about Rubin. It's a observatory that's just about to be finished in the next year and a half or so, that will conduct the legacy survey of space and time, tremendous astrometry, tremendous depth. And I think most interesting thing for us in the solar system is it will start in a little bit less than 2 years from now. So let me lead with the headline. These are the kinds of things that we expect Rubin will enable us to discover. So in the left-hand column, there are a number of different classes of objects in the solar system, and then the number that are currently known. And I apologize if these numbers are slightly out of date because we keep discovering new ones, but they should be corrected within 10%. And then the number that we expect with Rubin, and most of those numbers in the column, in the middle column, are going to come in the first 3 years or so of the survey. So if you just look at it, it's about 25,000 known NEAs. It's going to go up to 100,000. Number of known band belters is going to go up by a factor of 5. Jupiter Trojans are going to go up by factors of 20 plus, and so on. So this is why I think this is an interesting survey for those of us who are working in the solar system, just because we're going to get populations studied at, or samples from the population at an unprecedented scale relative to what's been out there so far. Here is the current schedule. You can see this schedule if you go to ls.st/dates. I've just excerpted a couple of key milestones. The 3 that I'd like you to focus on are the 3 that are underlined. So we're going to have engineering first light with the commissioning camera in July of 2023. So that's less than 1 year away. And then the system first light with the large LSST camera in March 2024, followed by by commissioning of the large camera and the end of verification surveys by July 2024. So this machine truly is about to begin in something like 2 years from now. Let me talk a little bit about how Rubin will find asteroids, because if you're involved with asteroid work today, it's going to be slightly different than what's typical. So to recap how asteroids are found, if you look at a single image of the sky, an asteroid looks exactly like the star. That's where the name comes from. It looks star-like. The way you find it is by looking for their motion. So if we take a couple of images of the same area of the sky, we're going to see that object moving. And in the right-hand plot, you can see that. In the right-hand image, you can see that one object shifting around. So today, the way these objects are discovered is we take 3 or 4 images per night. That's enough to uniquely, unambiguously identify objects that go together and find what's called a tracklet and report it to the Minor Planet Center. The problem we have with Rubin is twofold. One, Rubin is not a dedicated asteroid survey. It's not there just to do asteroid science, but it's there to do all kinds of science in addition to the solar system. And coming back to every field 3 or 4 times per night would be prohibitively expensive in terms of the reduction of the area we could cover in that one night. So what we're going to do is we're going to come back to every field in the night twice. So we're going to have tracklets with only 2 observations. The second problem is that Rubin is much deeper than what we typically have today. So it's going to go down to 24th magnitude or so. At those depths, the density of objects further goes up. So those pairwise detections or pairwise tracklets are not only going to be more difficult to associate in the first place, but there are going to be many more of them, and we're going to be associating them by accident with things like artifacts in image processing, or just objects that happen to be adjacent to each other. So each tracklet discovered in a single night with Rubin is going to have more than 50% chance not to be from a real object, but just be a chance association. The way how we're going to find those that are due to real objects is we're going to take all tracklets collected over a period of about 2 weeks, and then find triplets, find 3 tracklets, each tracklet with a pair of observations that when you fit a Keplerian orbit to them, that the result of that fit comes back. That fit that fit produces a good fit. So this is different relative to what's being done today, where you identify a tracklet that's essentially 100% certain to be coming from the same object. You submit it to the Minor Planet Center, and then you let them do the linking. In our case, individual tracklets are going to have very low probability of being real, but we ourselves are going to do the linking over a window of something like 2 weeks. Once we establish that link, at that point we know that the tracklets involved in the link are real, and we send all of them to the Minor Planet Center. So the upside is we're able to use a mission like LSST to find a tremendous number of asteroids. The downside is that you're going to get these discoveries with a delay of a couple of days relative to when the first tracklet appeared, just because that we don't know that first tracklet is real until the third one comes in. So let me talk a little bit about how this is done. The algorithm that will link those tracklets is called HelioLink. And the way it works is or what the challenge is here is if you have millions of tracklets every night, how do you identify those that go together over periods of 2 weeks or so? And the way we do that is by using this the algorithm called HelioLink, which linearizes motion of objects in the sky by assuming a certain distance and assuming that and reprojecting them to a coordinate frame observed from the sun. So to explain what that is, assuming I can find a pointer. So here's an example of a typical main belt asteroid and what its trajectory looks like in the sky. It's the thing that I want you to notice is that it's curved. I am cheating a little bit here because the y-axis is significantly exaggerated relative to the x-axis, but you kind of get the gist. However, if you just try to take this tracklet and linearly extrapolate it, for example, to the time when this tracklet appears, you will completely miss it because you're going to extrapolate it down somewhere here and not up here. So you won't be able to, with linear extrapolation, go from here to here. Oh, I think PowerPoint stopped again. You'll have to refocus it. This stopped working again. Can you click on PowerPoint slides again? Yeah, I think when you change Zoom, you unfocused it. Do you mind if I go do it? All right, now it works. Thank you. So instead, what we do is we can change the point of view. The reason why this happens is because both the asteroid and the Earth are moving, and that's why you get this complex motion in the sky. So what we can do is we can change our point of view to the sun instead of the Earth, therefore removing one side of motion and getting something like this that is now a linearized trajectory. And then once you have this linear trajectory, you can basically project any tracklet to an epoch of any other tracklet, run a clustering algorithm, and discover it that way. And so what I tried to summarize here is an algorithm called HelioLink, introduced by Matt Holman and company back in 2018. The details are in the HelioLink paper. Does it work? It does. They managed to link over 200,000 objects in the isolated tracklet file by doing this kind of realization and projection. And so we decided to do the same. So for Rubin, we have two improvements, I think, or one critical improvement to this algorithm, which is in the original paper, what Hallman et al. Did was they would basically reproject the sky to what it would look like if it was observed from the sun, and then in these sky plate coordinates, propagate all the arrows, all the tracklets to common epoch, and then look for clusters on the sky. That's great, that works, but you have confusion. Like, for example, in these regions where you're clustering objects that might be potentially both nearby and farther out, and they all fall in this 2D projection, they all fall in the same place, and you cannot tell which one is which. So one of the things that we've done, we realized that you don't actually need to do the clustering in 2 dimensions, you can do the clustering in 3 dimensions. So you're basically, given the tracklet, you're assuming what the orbit of the object is. You can propagate it not even linearly, but using a Keplerian approximation, which is fantastic over the 2-week period that we use. And then look for tracklet, you look for clusters in 3D space. And here's an example for an Inno AMOR and for a main delta Hygeia. So does this work? Oh, the wrong way. The answer is it does. We've written this code. It's publicly available. We've been running it on LSST simulations. We're getting completeness up at 90% level. Our requirement is 95% level. Our Inno discovery performance is at something like 70% now, but that is before tuning. So we expect to get that up to 90% or more as well. And in all cases, it's very high purity. And the beauty of this algorithm is that relative to old style MOPS algorithms, it scales as n log n. So we have a code that will work. It'll work on Rubin. It will discover asteroids in a slightly different way than they're discovered today. But we're able to do it in a computationally cheap way. So we can essentially get this done on maybe a few machines rather than a cluster as was originally predicted. These were all simulations. I love simulations, but I don't trust them. So we also tried to run this on real data. So here is running on data taken with DECChem using the DECCATS project, which is taking DECChem data to the depths at a cadence roughly similar to those of Rubin. And we've been running HelioLink, our implementation of HelioLink on this, finding objects as well. So these are just some objects that were discovered that way. And we also ran it on Atlas data, and we're able to recover all of their discoveries. So if you're interested in this code, here is the link. I think we'll share these slides, so you'll be able to just go and click on it. It's installable, it's runnable, and I think it's going to be useful for more than just Rubin. But anyways, I would just wanted to give you a brief intro on how Rubin is going to discover asteroids, because if you see what it will do and you see the cadence, you might think that this is not going to be possible, but in fact, it will be. All right. So now let's talk a little bit about data products and about the products that we're going to be delivering for Rubin Science. Here is a diagram of one night as it will look for Rubin Observatory. So during the night, we have this big block that I just marked observing. This is when the telescope observes. There are going to be an order of 1,000 images taken each night. And during observing, every image that is taken is going to be differenced within 1 minute of observation against the deep template. Any objects identified, any objects on that difference image identified, and those objects could either be things like variable stars or AGN or supernovae, things that have changed brightness, or things that have moved, asteroids. For asteroids that are known, we will immediately associate the designation of that known asteroid to the observation. And as soon as that observation is published, again, within 60 seconds of observation, if that was a known asteroid, you'll be able to get that piece of information. Objects that are unknown, go into this datetime box that runs linking with the code that I just described. So at datetime, we take all the data from previous 2 weeks and then try to find objects that fit Keplerian orbits. Those that we discover, we submit to the Minor Planet Center. Minor Planet Center verifies that they are correctly linked, and a new MPC orb catalog is produced. All of this happens in daytime. When that new MPC orb catalog comes in, we compute some what we call an internal daily data products release, which computes things like absolute magnitudes and so on for all the objects, and get ready for observing in the next night. And this basic loop then repeats 3,300 times over 10 years. So at every point where there are letters in this previous diagram, a data product is produced. So at nighttime, within 60 seconds, Rubin is going to send data on everything that has changed in the sky in that observation. And part of that alert is going to include things like PSF flux, aperture flux, including trail source fit. So we'll know objects that are moving and how fast they're moving. And for all the known objects, these will be associated with a designation. So if you're working on something that requires the knowledge of some interesting change in an asteroid immediately, and the classic example here are active asteroids, this is how you'll be able to get it. So you just compare the predicted, for example, predicted brightness of an asteroid to what has been measured in the alert. And if the brightness is off by a couple of magnitudes, you're pretty certain that it has that you're seeing activity. So that's the primary use case for these data products. In the daily catalog, we'll be producing orbits. These will be computed by the Minor Planet Center. Light curve characterization. So because each object is going to be reobserved on order of 80 times a year, we'll be able to compute quite nice light curves. Our cells will be fitting periods, light curve shape, and other features of light curves. We will not do full shape modeling. I want to emphasize that. We'll be also estimating absolute magnitudes, things like MOID and extendedness indicators. So where there's evidence for whether an object is extended or not. And so with these data, you'll be able to do things like this. So this is an example from a simulation of an asteroid, of a phase curve for an asteroid. Here's phase angle versus distant corrected R-band magnitude and the best fit. And this is the sort of thing one will be able to do for more than 5 million objects in the catalog. And then every year, we're in essence going to repeat this, but with improved photometry, with much better understood algorithms and software to produce sort of a gold version of a catalog that is useful for population studies on a yearly basis. I can talk more about this in question time if you want me to. This is a quick diagram of what is going to be available and to whom and when. So alerts are public essentially immediately within 60 seconds through alert brokers. Since we submit all of our photometry and astrometry and orbits to the Minor Planet Center, those are effectively public as well within a day. And then added value products like absolute magnitudes, light curves, light curve periods, and so on, and the data release orbit catalogs are within the LSST archive, so they're available to data rights holders and otherwise proprietary for 2 years. The last thing I want to mention is how do all of us prepare for science? And there are 2 parts to this. One is we have simulations. We've built a simulation, full 10-year simulation of the survey and solar system objects that you're going to be able to, that the survey is going to find. This is just a list of what's in the simulation right now, but it should be fairly realistic. One thing to note is that it doesn't include false positives right now. So you could generate those yourselves if you want to, test different linking algorithms and similar. It's been done by using a tremendous amount of community developed software, including software from Shantanu Naidu, from Steph Merritt, who's going to be talking here, from Meg Schwamb, Siegfried Eggl, Grigory Fedoritz, and a number of other members of the team. of the broader solar system science collaboration, as well as numerous undergraduates who have helped get all of this, pull all this together. So this is a wonderful example of collaborations that you can enter in the SSSC. Here's an example of one of the things we've done recently with this simulation. We've looked at what happens to the Inno confirmation page once LSST is in the sky. And in the interest of time, I'm not going to go through everything except say that bad things happen. Bad as in good, depending on your point of view. The Inno confirmation page right now gets on order of maybe couple of dozen new objects to follow up every night. That's how many potential Innos are discovered. Using the same criteria with Rubin, we are going to be, we might be sending something anywhere between 1,000 to 10,000, depending on where the ecliptic is, potential Innos every night. So this is one thing that we're trying to understand how not to do this, how to really restrict ourselves to maybe the most interesting Innos, because right now the follow-up system does not have the capability to follow up all of this. But these are the kinds of things that you can do with the simulation. How to get access through SSSC Jupyter Hub. We have this whole database is there in a Postgres database. It's also available on request as about download. And if you want to start playing with this, go to link-hub on LSSTC Slack, and just ask for an account. We'll just need your GitHub username, and that's it. All right. So the second part is about preparing for the sciences, is the community aspect of it. I already talked a lot about solar system science collaboration. Meg, do you want me to talk about this? Or? All right. So these slides were contributed by Meg Schwamb, who's one of the co-chairs of the collaboration. Solar system science collaboration really gathers all of us who care about LSST as a solar system discovery machine. It has a number of active working groups. You can see all the leads of different working groups. They're all working together to prepare the necessary software and science and thinking, and really the community for what's coming up with Rubin. I want to emphasize Laura Inno, who's our cross-science collaborations, equity, diversity, and on equity, diversity, and inclusion committee. Laura is here. She'll be giving a talk later as well. The collaboration does is the main purpose is to facilitate conversation and to connect members during these last 2 years, as first data are going to start coming in from commissioning, and we get ready for science. So if you want to know what's going on with LSST and get involved, this is a way to do it. Here's an example of something collaboration did, was to provide feedback for cadence simulations. How exactly LSST is going to cover the sky is something that hasn't been decided yet. There are numerous test cadences that are being put out, and we as a collaboration look at them, comment on which ones are better for solar system, which ones are worse, and what to do and what not to. And here, for example, is a product of one of that huge piece of work that Meg led to tune the LSST observing strategy for solar system science. All right, so I'm going to stop here. If this sounds interesting, please join the LSST Solar System Science Collaboration. Go to this website, lsstssc.org. I'm actually afraid to try to expand that into what it spells. It's a huge acronym. But go there. There's a membership button, and you can sign in, and you can request membership if you're not a member already. All right, so I'm going to stop here and ask if there are any questions. Thank you. All right. Let's start with either Zoom or Slack if there are any questions.
Thank you. So the question is from Fabrizio. How effective and fast is LSST to detect very close targets, which may be imminent impactors?
So we are going to be able to detect everything to, I think, about 30 degrees per day. Everything moves to about 30 degrees per day. The Rubin itself will not do anything special with those objects. They will be sent to the minor planet center. JPL will pick them up from there, and then the normal community process will take over. So if you want to monitor which fast movers come out of Rubin, you can either directly connect to the alert stream and look for objects that move with that speed, or you can just wait on and look at Sentry that the JPL operates. Any other questions from the audience?
Hey, are some of the simulated data you are speaking of available to the public or not? At least some of them.
So this data set is definitely available to the science collaborations, and I'm looking at Meg now. Do we know if it's available to anyone?
My understanding is it's not. I might need that one. So it's not publicly available to everyone. I think theoretically it might be. That might be a question of whether it counts as proprietary. But I think if you have data rights, then it's very easy to get access through the science collaboration. If not, I think that could be discussed whether that should be public, probably with Mario, and just double checking that it's not considered a project or operations data product in any way that would be proprietary. So, but I would say the easiest way is join the science collaboration, then you get the GitHub and the Jupyter Hub access.
Yeah, if you have data rights, you've got access to it. If not, then we have to talk to Bob to figure out if we have any constraints on it. Yeah. All right, thank you. Well, let's move on with the program, and I believe next is. Do you know who's next? I think it might be Laura. Yeah.
Thanks. There's a little bit of echo. I don't know if do you have problem understanding what I say? Because there was a little bit of echo where I was seated, but I thought everyone understood. So yeah, okay, sounds good. It's not sure. Is that a problem for Marcella? Can we remove the mask when we speak, or? Okay, sounds good. Yeah, okay. Okay, yeah, it's really nice to get to meet some of the people I've been interacting with in the past few years. It's nice to be here, and thank to Mario and Meg for allowing me to give this presentation. As you can see from the title, it's not really a science talk. It's more like I'm taking this opportunity to introduce the work that we are doing, that we are planning to do for our in-kind contribution to the solar system science collaboration, and the work we started doing in preparation for that. That's the should this change slide? You need to. Okay. Anyway, so there is a session on in-kind contribution, but I will just start by mentioning briefly the framework, and then outline the contribution we are planning to submit, introduce the team, and then the work we are doing, hopefully. Okay, so as you may know, Italy has been interested in LSST from the very beginning, and after all this time, the effort coordinated by the National Institution for Astrophysics has been formally approved since earlier this year. And among the different contributions, which are mostly in the form of directable, software directable contribution, there is one also from the team I'm coordinating. And this is the only one directed to solar system science collaboration. And we sketched this 3 years ago together with Meg, David, Mike, and Henry. So basically we tailored the contribution on what we thought were the needs of the collaboration, and of course the expertise already within our team. We are traveling with 1 year of delay because of the COVID, so we hope that we will be able to advertise the job position in the beginning of next year. And of course, the contribution itself, the content of the contribution is not set in stone. We will fine tune it together with the collaboration, and we are going to do that as soon as we get the funds from enough. Okay, so the basic idea behind our contribution is to provide a pipeline that will work on every single image of LSST that will include solar system object detection and perform all the different techniques to characterize these objects that are not within the standard pipeline. So for instance, determine the position of the photocenters, measuring the degree of their circular symmetry, and so on and so forth. And also one of the deliverable will be also the forced photometry of the faint objects, because we want to try to detect the activity, active bodies as early as possible, even a low signal to noise ratio. And then we think we are going to have a second pipeline that will run on a subset of these images, the one in which there is an active object. And we will provide the characterization of this activity level, which means basically giving measurement of the tail and trails of the comet and the dust properties. Especially, we plan to estimate the dust loss rate by using a model that has been developed by our team. And this brings me directly to introducing the team involved. So the team has a core team, which is basically me, my colleague Ivano Bertini at the Partenope University of Naples, and Marco Fulle in Trieste. He is the main physicist behind this theoretical model that I will explain in a little bit. As you can see, some of the names are colored. That's because they are also involved in the ESA F mission Comet Interceptor. And when I mean involved, basically means that they are playing a role in the building of 2 instruments, DISC and ENVIS, which are part of the payload for the spacecraft. I'm assuming most of you already know this about this mission, but just for the one who don't, this is a mission that has been recently approved and moved to phase 2 by ESA. And the main idea is that we want to intercept comet either from the outer solar system or the outer space. So in one case, we want to probe the material from which solar systems in our neighborhood are formed in a galaxy. In the other case, we want to get information from on the protosolar nebula. Of course, I'm mentioning this because I'm just to say that, of course, our team is interested in the science objectives that are in support and complementary to the space mission, which means, of course, the selection and the characterization of the potential target, the statistical understanding of the underlying population from which to which the target will belong, and possibly the follow-up in order to study the dynamical evolution. Of course, LSST is going to play a key role in all these aspects. And this is, I think, very well known, and there are several members of the collaboration that are also involved in this task. But what we can do now to prepare for that is to start to focus especially on the second and the third task. And we can do that by starting to observe long period comet with a smaller telescope. So we basically started a campaign that will serve as a test bed for the pipeline that we want to produce, and also for the theoretical model I mentioned before. Sorry. which is especially useful to understand the activity beyond 4AU, because LSST will find comets at much farther distances, and you know, at this distance, water, the pressure from water vapor is expected to be too low to actually produce the dust ejection. Okay, so so the first result from this campaign has been already published in the paper Full et al. 2022. These results are based on images taken at the TNAG and the Loiano telescope. And basically what are we doing with this is to fit the observed isophots, which are the gray lines, with the theoretical isophots, which are produced on the basis of the probabilistic tail model by Marco, that has already been published in also this work here. And from the fit, we get the dust velocity at the and the afro, and even the dust loss rate. Okay, one important point is that the fit only depends on 3 parameters, which are all correlated to the nucleosides. So this model can be really easy. It's easy to be rescaled to the size of LSST images. And there are some other science outcomes that we can maybe discuss during the question later. So the photometric observing campaign is going on. These are our students collecting images at the Asiago telescope in the north of Italy. And the second paper is in preparation. I just wanted to mention as a final point that in order to improve our statistical understanding of the population, it's really important to detect them with the LSST as early on as possible. And to this purpose, I'm co-supervising a master thesis project of one of the machine learning students at Partenope on using a machine learning approach in order to detect slow moving objects. But he's going to present this work in the poster session later. And also, he is also giving a talk in the next parallel session. So concluding, we really look forward to start working on shaping and fine-tuning the contribution to the solar system science collaboration. So with you guys, basically. And for now, we found that the results from the application of the probabilistic tail model makes it very easy to use on future LSST images. And we also find that, but this is kind of a spoiler, machine learning techniques are very painful, but very useful and promising for the detection of farther fainter objects at the LSST detection limit. That's all. Thanks.
Are there any questions? I've got one. So can you give a timeline for the tools that you're building in terms of your sort of in-kind contribution? So what do you expect to have and when, roughly? So, you know, you say about this tool, but is that like something that's Conda installable that I can run on my laptop, something that'll run on the science platform? What are you thinking? Can you give a little bit more detail about timeline of deliverables?
Oh, well, so this is a software directable effort, so we will comply to what will be the needs, but I mean, you probably in Python or everything that will be the most flexible. And if it has to be merged in the pipeline or in the standard pipeline, or I don't know, it will go in the data flow, then of course we will respect all the requirements. So the idea is to hire a software engineer person, so someone who is really has skills to actually build the software and with our guidance, but someone who knows how to code professionally. Sure, go ahead.
You're talking about raw LSST images. I assume you don't mean raw LSST images, but do you mean direct images or difference images? because there's quite a big difference on what the artifact level and what the calibrations may be and things like that.
So for now, we are using basically a simulated sample. We are using the data previewed 0 images, and now we are putting our object.
So it's not difference images. It's
no, it's so it's data preview images. So that's the CalExp, right? So it's
just quickly.
okay.
I think everybody working on the solar system should think really seriously about working on the difference images. These fields are really pretty crowded. They're down to 24. They're very different from the sort of fields you worked on before. The difference images should be pretty clean, and you get rid of all the static sky artifacts, including all those pesky galaxies. So I would strongly consider investigating the diffems rather than the CalExp for any of your solar system work. There are other systematics you'll have to learn about, like kernel size implications, but I think that's where you should all be starting.
Yeah, no, that's a great suggestion. So the reason why we went for that is that we are using 3D CNN, like work on the images, and basically we are using very small cutout, so 15 times 15. So that's, and basically data preview 0 is not that, for now we didn't have issues on that, but I understand the point. I mean, eventually that will be good, but on the other side, if we can get without DIA, then we can get alert detection since day 0, right? But yeah, thanks.
Let's think Lara again. So our next speaker is, I believe, Steph Merritt.
That's not the updated one. Those are the wrong slides. It should be a V2.
V2?
Yeah.
Ah, yes. Yes. It's
That's me. Sorry to be a bother. Okay. Awesome. Okay, hi everyone, I'm Steph. I'm a postdoc at Queen's University Belfast, where I work with Meg and a whole bunch of other people on a survey simulator for solar system science for the LSST. So thank you. So what's a survey simulator and why do we need one? Well, all surveys have biases, astronomical biases, from the optics, the instrumentation, the cadence, the location of the survey, often quite complex and intertangled. If these biases are well understood, then a survey simulator can be used to understand the effects that these biases have by running it on synthetic populations and comparing the output to actual observations. So this is a technique that's already seen a lot of use in solar system science, specifically with trans-Neptunian objects. So it's been used for the debiasing purposes in OSOS and also the dark energy survey. And it's really useful for just getting statistical information about the underlying populations without that bias getting in the way. And this is going to be especially important when it comes to the LSST, because as we know, there's going to be millions and millions of discoveries. We have this unprecedented opportunity to do population studies on small body solar system populations, but we can only do that accurately if we understand the bias. Oh. There we go. So one particular case study I'd like to highlight is the fairly well publicized case of Planet 9, where extreme trans-Neptunian objects have purportedly we've kind of seen purportedly seen a clustering in their orbits, which has been proposed to be caused by Planet 9 shepherding them onto those orbits. But it has also been suggested that this is due to an observational bias, that we are seeing these orbits because these are the ones we're more predisposed to see. The LSST is going to be uniquely positioned to actually disentangle this problem. It will detect extreme trans-Neptunian objects. And by using the survey simulator, we should be able to detect that whether that we're seeing a biased population or whether that this clustering is actually a thing which is happening in physical reality. Also, it's possible that the LSST could detect Planet 9 itself. So here we have the proposed positions of Planet 9 colored by probability. And then under the yellow space here, or this dark gray area, this is the LSST's field of view. And you can see that most of the proposed positions of Planet 9 actually lie within the LST's field of view. So with the survey simulator, you could feed it a list of proposed synthetic orbits for Planet 9, all of these probable orbits you think it might have, and you will be able to output what you might actually see. So you'll be able to see when Planet 9 could be detected, in what fields, in exactly what time. So that brings us to our survey simulator. So the survey simulator that we're building is completely open source. It's built in Python using pandas, and it is generalizable and completely modifiable. We've built it to be extremely modular, to be extremely customizable, both by users who just want to change a few things in a config file, and for more advanced users who might want to include their own filters. And one of the really important points about it is it will be applicable to all solar system small body populations. Previous survey simulators have focused on a small subset, such as near-Earth objects or TNOs. We have built our survey simulator to cover every small body population, every possibility that we could think of. So any science case you can think of, we should be able to cover it. Another bonus is that it's actually built as a layer over an ephemeris integrator. So this part here, where you actually integrate your orbits and detect whether they actually lie in any of the pointings of your survey, that's the computationally expensive part. You only need to do that once. Once you've done that, you can run our post-processing layer, survey sim PP, and you can run that many times as you like. So you avoid having to do the computationally expensive part more than once. Okay, so I'll give a brief overview of how it works. It's essentially divided into two different sections. In pink on the left here, this is where we do calculations of magnitudes and uncertainties. And then in yellow on the right here, these are our filters. And we call them filters because they essentially cut out a subsection of the detected objects. These are all customizable by the user. They can be turned off and on, and they have various parameters that can be controlled by a config file. Okay, so inputs. You start off with the output of your object ephemerises and your associated fields from something like objects in field or a similar code, something which tells you which of the pointings your objects are appearing on and when. You also feed it the pointing database. So that can be an actual pointing database once the survey is running, or we're currently using the simulated ones from RubinSim. You give it the object orbital elements given in either Keplerian or cometary format. The object physical parameters, so currently that's H, the absolute magnitude, any color offsets, so G minus R, I minus R, etc. And then any phase coefficients for the phase model you might want to use. Also, as an optional input, you can include cometary activity information because so many solar system small bodies are showing cometary-like activity. So you can include AF rho and K in that as well. We then calculate the magnitude for the user-selected phase model. So we have linear, HG, HG1G2, HG12, or none at all if you like, taking into account the distance, the phase angle, the filter, and any cometary activity. That magnitude can then, if you choose, be adjusted for any potential trailing losses. So if you're studying near-Earth objects, you can then adjust the apparent magnitude to basically account for the fact that so much of your flux will lie outside of the PSF fitting kernel. Oh, wait. Yep. We also then adjust the 5 sigma limiting magnitude for each observation at each source based on vignetting. So the darkening of the field at the very edges due to the telescope optics. And then we calculate the signal to noise ratio plus the photometric and the astrometric uncertainties. So once these calculations are made, we simply move on to the filters. So the first filter we have is the footprint filter. Now, this will basically tell you, does the object appear on the camera footprint? This can be a very simple circle if you like, or we do have the more detailed LSST footprint, which includes the chip gaps and the raft gaps. And if you have another one, another footprint that you would like to include for a different survey, you can create that yourself and include that as well. Then you have a choice to either remove all detections below a defined signal to noise ratio or all detections fainter than a defined magnitude limit, or neither. Also, we have a detection efficiency filter. Detection is probabilistic, especially at the faint end with a decreasing fading function. You don't have just a step function at your limiting magnitude. So we use the analytical equation from Merritt and Micheli, which is dependent on the simulated seeing and according limiting magnitude. That's parameterized by fading width, which again, you can configure yourself. You can also choose to remove any detections brighter than a defined saturation limit. And then we also have a filter which mimics the effects of the solar system processing pipeline for linking solar system objects that Mario spoke about earlier. So you can set this yourself. It does default to the standard defaults that Mario was mentioning, but you can set the minimum number of observations to form a tracklet, minimum number of tracklets in a track, minimum time period for track construction, object separation for the tracklet to be detected, or you can turn this off entirely, or if you're an advanced user, you can replace it with your own algorithm. In the end, what you get is an output. So this can be a CSV, it can be a SQL database, it can be a HDF5, whichever you're most likely to work with. It outputs all of the detected objects with their ID and location, the field ID, location and filter of the observation, apparent magnitude and filter, the astrometric and photometric uncertainties, and the 5 sigma limiting magnitude at the object position and field center. So we are currently in final validation and checks, so we don't recommend you use it for your science cases just yet, but it will be coming very soon. The QR code will take you to the GitHub repo, though. If you want to beta test it, have a go, see how it runs on your own machine, see how it runs on your supercomputer. And there will be an upcoming paper by my colleague, Giovanni Federico, that's in prep, and we hope to get that submitted by the end of the year. That's everything. Are there any questions?
Someone's typing online, so there might be a question. I have one. No, I can use this one.
Okay.
In terms of the software, what can you talk a little bit more about the modularness of it? So why it's built the way it is in terms of sort of filters and functions?
Yeah, every single filter is a self-contained function by itself. So if you wanted to create your own, it would just be a matter of writing a simple function in Python and then inserting it into the code. Also makes them very easy to turn off and on using a config file.
I'll remember to say my name this time. I'm Robert Lupton. When your detection limit, how do you model the effect of crowding? I mean, in theory, it's just signal to noise from the background. In practice, things aren't always quite so nice. So if you're trying to find planet 9 down in Sag, how do you predict the magnitude limit to a particular place?
Oh, wait.
So this isn't done explicitly. This is rolled into the detection efficiency fading filter. So when it comes to crowding, that detection efficiency is supposed to basically involve a lot of effects which can contribute to an object not being detected. So crowding is not something we're dealing with explicitly. It's something we're dealing with probabilistically, if that makes sense.
So I have a comment question on that. So it's not explicitly because we're assuming you're looking everywhere else in the sky because we're doing the easy case. You can make your own function to do better crowding. So the point is we're allowing you to do all these things. You can just add in a function that does either better depending on what you want to, how you want to deal with the crowding specifically in terms of how that messes with your limiting magnitude. So we haven't explicitly done that bit because it's getting everything else running. But the idea is that then somebody can go in and write, this is how exactly I want to handle crowding or apply a crowding to decrease detections. So it's built in the functionality. Yeah, we'll get there. If somebody could really fund this full effort so we could do it, we would totally do that, but it's partially unfunded right now. Most of us are not most of us aren't funded to work on it. So we hear you, but the idea is that we got to get everything else working since to do that.
So we have to move on, unfortunately, but there's probably later, so we can still ask your questions. Thank you again. Okay, Marco is next.
Looks like it's not clicking anymore. How do I, what is it, that one? It's that one. Okay. Okay, so no, I'm back. Hello, my name is Marco Micheli. I work at ESA's NEO Coordination Center, which is actually pretty close to here. It's in Frascati, near the main ESA center called ESRIN. And I'm part of a group of a few people that in that center work on near-Earth asteroids at this place called NEO Coordination Center. And we do a few things which are part of ESA's broader planetary defense program. The planetary defense program is an agency-wide program, not just here in Italy, that does basically these three things that you see here. We try to detect asteroids, which is the part that is more relevant for the audience here, but I will go into much more detail on that part in the rest of the talk. Then there is a section called assessment. Basically, it's the use of the information that comes from detections of asteroids, astrometry, not both our own and the one we get from the Minor Planet Center, to assess the threat that specific asteroids pose to the Earth. And the last, and I will briefly mention a little bit of that at the end, the last one that I'm not going to deal with today is mitigation. So basically, once we know that something is actually coming towards the Earth, what we as scientists, but as space agencies and humanity in general can do to mitigate the threat from an asteroid. But as I say, I will mostly focus on this part, detection, because of course this is a telescope meeting and this is actually what I do. Detection of asteroids is basically two things. The first one is what mostly LSST is designed to do, is surveying, so it's discovering things in the sky. ESA is so far not doing a whole lot on that, but we are working on it. We are developing a few telescopes that are designed specifically to cover niches that are a bit different from what somebody like the LSST team is doing. The main one will probably become operational in about a year or two in Sicily. It's called the FlyEye telescope. It's a way smaller telescope than LSST, of course. It's a 1 meter telescope, but it's a very wide field and it's designed to discover what we call imminent impactors, meaning asteroids that are coming toward us and they give us a very short warning time because they're basically in the direct plunge toward the Earth when we discover them. And we are also developing other telescopes. These are just mentioning them because one of them is in Chile. They're much smaller telescope again, but these are designed for a variety of uses, not just asteroids, but they include the fact that we will use them soon to do low elongation surveys. This is again something that I don't think LSST will do a lot, pushing very low over the horizon, very close to the sun, like 30, 40 degrees elongation, to try and discover things that just happen to stay there because of their orbit geometry. So this is just a broad idea of what we will do soon for discovery, but actually the main thing we do today and we will keep doing and may have relevance for LSST in the future is follow-up. We have developed a network of telescopes that some are ESA's telescope, but most are actually under contract with ESA, that are literally all over the world, try to cover all the possible hemispheres and longitudinal positions, with the idea of being able to provide follow-up of asteroid discoveries on very short notice. very short notice for us may actually be sometimes minutes to hours, basically on a periodicity that is shorter than the rotation of the Earth. Anything that has to be observed before the Discovery Station is night again, so before 24 hours. Anything that requires much faster timescales than a day. So this is what we've developed. This is just some of the telescopes we have. The rest of the talk, I will mostly tell you what we do with these telescopes. I try to limit myself to the aspects that have a connection with LSST. Of course, with the other things that are more related with maybe imminent impactors or brighter objects that we observe. But this is basically what we do. Is just, I'm not going to read the whole thing, but there are a few things that are of relevance. For example, the second point there, the fact that we do use some telescopes to do what we call extend follow-up. So choosing high priority, high profile targets that are particularly interesting for some scientific or planetary defense reason, and follow them up for as long as possible with the biggest telescopes in the world. Then, well, the other things just gonna show to you in examples. This is just a handful of cases of things we have observed. This is something that was mentioned before, I think, by one of the questions, what we call imminent impactors, meaning objects that are found and need to be observed right now because they're gonna hit us very soon. Very soon means hours from discovery. This may be something that I don't know how LSST will actually exactly deal with, but we do stay prepared for when these cases happen. And this is the case. This is just an object that impacted in March in the Northern Atlantic Ocean. The reason why I'm presenting it is, again, to show the timescales of what we do. This object was discovered by the Discovery Station less than 2 hours before actually impacting the Earth. So we have to react really on timescales of minutes in order to do something for cases like this. Here we're getting a bit closer to what LSST will care about. And it's the other part of what we do is to go really faint with some of the biggest telescopes in the world. We have an agreement with VLT to chase high-risk objects that have a very high impact probability or pose a high threat for a future possible collision with the Earth. And the idea is to, of course, go very, very faint. And VLT is, of course, a large telescope. It can go extremely faint, and we are pushing it to the limits of what we can do on an asteroid. And this is just an example of a detection of something of magnitude 27. At the moment, we have a limited number of hours per semester to do this because we don't have a lot of high priority impactors. But of course, in the LSST era, this will become really prominent because, of course, there will be a lot of faint asteroids discovered. This, on the other hand, is just an invitation for people who have smaller telescopes. It's something that most people doing follow-up don't think of. If you have, this is an experiment we've done with an 80-centimeter telescope, trying to push it to the limit of what it can do on asteroid follow-up. And an 80-centimeter telescope, if you spend half a night on it, can go fainter than magnitude 24. So this will be where LSST discoveries will be. So this is where we will definitely need a lot of follow-up. And most people don't consider that meter-class telescope can actually do it for high-priority targets. It's a lot of time. It's a huge investment, of course, of time. But time of small telescopes is actually cheaper. So I recommend people to think in this mindset too. This is actually not particularly important. It's just the idea of campaigns to do things together in the world, but I'm just going to fly over. This is another thing I actually wanted to point out. This is a slightly different approach to when there is a threat for an asteroid that is about to hit the Earth or possibly hit the Earth in the future. And it's what we call negative recovery. It's the idea that if you have a possible threat from an asteroid, but you cannot find the asteroid because it's lost, because the orbit is too poor, you can actually point at the part of the sky where the asteroid would be if it is exactly in the orbit that leads to a collision in the future. And if you go very deep and you can exclude for sure that the asteroid is not in there, you've excluded impact even without finding the asteroid. And I think LSST will actually find situations like this in the future, because you will cover areas of the sky where disposition of the impacting orbit will be, and you will be able to do these exclusions. I don't know if it's something that has been considered by the consortium, but it's definitely something that can be done with the powerful telescopes like the one we have, basically for free, because you just get to observe in that particular area. And then this was another thing that I can just fly over. This is basically the end product of what we do, is to take all this data, our data, the public data, the MPC, and in the future LSST data, to produce impact monitoring predictions, so predict impacts on the Earth of asteroids, both on short term and in long term. And of course, this is just a final slide that I'm just going to leave there. What ESA plans to do, of course, more telescopes of the same and of different kinds in possibly different locations, try to carve a niche that complements what LSST will do by going in other places and doing slightly different types of observations and be complementary. Thank you very much. If you have any questions, I'm here for you. Well, nothing.
I've got one. You talk about LSST, you talk about the fact that, in a few hours, which isn't necessarily doable since that's not reported to the MPC at that point, but there's also going to be things found further out that will be. And so I guess my question is, how is everyone coordinating? Because we didn't do really well with Borisov as a community, and that was something that was like, ooh, science. We didn't do a good job on the scientist side of communicating. And I know that on planetary defense, people have been thinking about this and sort of planning, but I guess thinking as a science collaboration member or co-chair, are we set up in the sense that the people that are thinking about this and people that have resources and Rubin are all sort of on the same page? Or how is this all going to be communicated so that if it is found by LSST and you've already followed it up and we now know more and more, how is that information being propagated? Because it seems like the planetary defense group community is very separate from most of the rest of the LSST solar system community. So I was just wondering how is this going to get announced? Am I going to hear about it on the news first or on some listserv or ATEL before, you know what I mean, before we know about it? So
yeah, I don't know exactly. I mean, I don't know enough of how quick the data flow will be. For the moment, everything goes through the MPC. The MPC is, it's the coordination, but it's also sometimes the bottleneck for anything that has to be fast reaction. So I hope that in the end, I mean, the planetary defense interest, of course, is very specific in terms of objects, but it's not very specific in terms of techniques and things we can do. So I hope that there will be a way for the planetary defense community, the observers that come from this side of things, to be able to quickly interact with people in the LSST team, so that whatever needs to be followed up for planetary defense interest, of course, is done, but also whatever can make good use of the resources we have. For example, I don't know, an interstellar object or something that has any peculiar interest for the science community. Of course, we will be very happy to contribute observational efforts and telescopes and all the time we can, of course. So I hope it will be done. I will, of course, try to stay in touch with the people here and do our best for this to really happen. Thank you.
Thank you, Marco. And this is something that some of us are from LSST are going to go and visit you at NEOCC later this week. And this is one of the things that we hope to discuss. Yeah. Well, we need to get ready. All right. Thanks, Marco, again.
I see that there's a question or a raised hand on Zoom. We don't have time for that, so please put it into the Slack channel and we'll get it answered.
Right. Unfortunately, because of time, I think we need to move on to our next speaker. I believe the next talk is remote. Is it Achille?
It is. I'm not sure if he's unmuted yet. So
hello, can you hear me?
We can hear you.
Okay, thank you. I was not able to switch on my mic. I'm sharing right now my presentation.
We're loading it right now.
Do you see it?
Yes.
Okay. Good afternoon to everyone. And thank you to Mario and Meg for inviting me to have this short talk. I'm here to speak on behalf of the Euclid Science Working Group, SSO. And here you can find all the names, not all of them, involved on this project. Just for those of you that are not used to Euclid issues, Euclid will do a survey of the sky of about 14,000 degrees square of the sky, skipping, of course, the ecliptic plane and the galactic plane. And it will arrive at about a limiting magnitude of 24. The typical survey will be a step and go survey. That means that in each direction of the sky Euclid will point and observe for a given time. For each block for each pointing, Euclid will observe 4 times, and in each block you will have a typical image acquired by using the VIS imager, plus spectroscopy, plus 3 images in the Y, J, and H band in the near infrared by using NISP. The numbers that you find here, the typical exposure times for the NISP are wrong. They correspond to a very old planning of the mission. In any case, since this is solar system objects is not the primary goal of Euclid, but since solar system objects are there, we are prepared to observe them, to disentangle objects from spurious sources that you have into the images. And apparently we can find objects up to a few hundred astronomical units. And we expect also to have objects at a very large inclination angle with respect to the ecliptic plane. This is the reason why using Euclid for solar system objects is very interesting, since this kind of objects are very rare. By the way, the typical pixel size of VIS and NISP are of the order of 0.0 arcsecond per pixels, and this means that we can get apparent motion larger than 0.2 arcsecond per hour, possibly. This is a typical simulation performed by Carey in 2018 in order to see for each population that we expect to observe with a typical rate in arcsecond per hour for the given population, which is the typical streak that you expect to observe into the VIS. And then if you detect this kind of object into VIS, you can use this information as a prior for NISP and get photometries in the Y, J, and H band for NISP. The number of total expected new objects discovered by Euclid during his lifetime, it is more than 10 to the 5 new objects. In this simulation, only 1% of the total observable SSOs are currently known objects. So there is a very large room for new discoveries with Euclid. Of course, at the first order, the solar system object spectrum is a typical spectrum from the sun, reflected by the surface of the SSO, but with given absorption bands, for example, due to the chemical composition of the objects. The key in disentangle between different kind of objects in the different population is to observe the object in different bands. This is why we are applying for observing objects with Euclid, and in this context, LSST would be very interesting for us in order to observe SSOs. By the way, this is in the simulation performed by Colin always in 2018, the superposition of possibly fields of view of LSST that can be used at the same time with Euclid in order to make this kind of work. Of course, what is the typical synergy between Rubin and Euclid in performing SSO science? Well, first of all, you are observing, if you can do this, you can observe SSOs from different point of the space. In this case, you can solve the distance by using standard parallax methods. And of course, LSST is much better than Euclid, but in any case, you can observe objects at the same time and in different bands. And in this case, you can get different information in colors, and you can remove systematics for the spectrum, for example, and due to the rotation. Since we expect to have numbers like this, 0. arcsecond per hour up to 1000 arcsecond per hour in the typical motion of SSOs, we prepared at least two kind of pipelines in order to detect this kind of objects. One which is devoted to slow motion SSOs, and the last one which is for very fast moving objects. The first one is based on the strict detect software. You can find information about this software in this paper by Mikko Pontina et al. And the second one is the SSO pipe, which is prepared and submitted as a collaboration for Euclid. And we got the referee response. We have something to do, but we are still working on that. But in any case, this is what you expect to observe. For very fast SSO, you expect to observe in different dithers. In this case, you have 2 dithers for Euclid, a very long streak of pixels illuminated for a very fast SSOs, and for a slow SSOs up to 10 arcsecond per hour, you can find a moving object which moves with respect to the foreground stars that you have in the Euclid images. This is how strict detect works. You start from a typical image as acquired by Euclid. You remove cosmic rays, apply all the corrections that you want, and then you produce a segmented image here on the bottom part, left part, on which you recognize all the objects. And we are confident to be able to get a purity of 97%. If you increase this percentage of detection at the cost of finding a large number of false positive, but in any case, there is the possibility to use strict detect with this procedure, multi-streak analysis, which uses the 4 dithers at the same time. And this is the SSO pipe, which comes in 2 flavors with 2 possibilities. Since we want to detect objects by using the images provided by Euclid, we prepare the pipeline by using level 1 data. That means that you use the data directly acquired by the satellite, you reconstruct the image, the full focal plane of the VC image, make the standard corrections, bias, dark and flat corrections, remove the cosmic rays, and then with a standard procedure, you use source extraction and scamp in order to get your list of candidate SSOs. Then you fit separately the right ascension and declination versus time. And for all the sources that have a good quality, you can estimate the motion, and you can flag it as an SSO and possibly deliver an alert. This is the purity and completeness of this kind of SSO pipeline by using directly in images. But in any case, I mean, this kind of a procedure lasts for at least 2 hours in order from the initial data up to the production of the catalogs on the 4 dithers. But in any case, one of the bottleneck here is scamp, which appears not to be so efficient. So we are studying now other solutions like astrometry.net and WCS Fit. And in the test that we are using right now, that we are performing right now, we are preparing to use another solution. That is to say, we rely on the catalogs as produced by OUVs, which is the organization that is devoted to the production of the catalogs, and which catalogs have a typical astrometry precision, relative astrometry precision of about 0.04 arcsecond, which means that we can do the recognition of SSOs directly on catalogs by using, for example, a pivot and input catalogs technique, which means that once you assume that one catalog is the pivot catalog, you can cross-correlate this pivot source with all the possibly associated sources in the other three catalogs and match which sources is the correct one by evaluating the typical calculation for velocity and direction into the sky, and you can get the correct association. This is what I'm saying. Blindly, for example, this is a test that was given to us by Luca Conversi from ISA. Blindly, we can run the code on a set of different catalogs without knowing nothing at all about the catalogs, and we are able to detect the objects. Why we are preparing to do this? Because, I mean, apparently the OUVs is very, they are very good in producing the catalogs, but we don't know exactly when the catalogs will be released. So we are in our pipeline, we opened the two possibilities. If we have the OUVs catalogs, we can run directly the search code in order to detect objects directly into the catalogs. If we do not have the catalogs as provided by OUVs, we need to have the same astrometric precision as delivered by OUVs. And in this respect, we found, for example, the WCS-FIT makes a very nice work because we have exactly the same median average astrometric precision as delivered by OUVs. And this is the typical status of the pipeline as installed right now in the ESAC server. We are able to detect SSOs. What we need to do right now is to merge the scripts and to produce alerts. And in this respect, Ben Macquarie is working on how to produce alerts to deliver to the rest of the community. Thank you.
I'm not sure if you can hear the applause, but there is a large round of applause for you. So thank you for this. Fortunately, we're at the time limit for the spot. So my suggestion is to everyone who has questions to put them into Slack and we'll get them answered there. So thank you so much for giving your talk remotely and telling us more about the Euclid LSST synergies.
Thank you.
And the last long talk of the session is by Giovanni Gronchi.
Thank you. I put this up.
So after Giovanni's talk, we're going to have the following talks about posters. So I think we'll go even into the like maybe 15 minutes. These initial technical issues.
How can I? Oh. Okay. So. Okay, so thank you. I would like to thank Mario and Meg for allowing me to present this topic. So we speak about a new method for initial orbit determination. So first of all, let's think about the classical method. The most famous classical method is the Gauss method, no? Which works with at least 3 observations. And at the time of Gauss, these observations were not more than 1 per night for the asteroids. And the equation for preliminary orbit determination by Gauss was a polynomial equation of degree 8.
Your slides aren't showing yet, so they're just online. So you'll just see them.
Sorry?
Your slides aren't showing on Zoom, so they're just adjusting it to the online participants.
So I have not to, I have to wait for, yeah. Okay.
I think you're good to go.
Yes. So, may I go on? Yeah. Okay, so the observation today are different. And for example, Mario in his talk showed that for detecting a moving object, you get some picture of the same portion of the sky, and you compare the motion of the object with the fixed star. This is an example in which we collect 4 detection, which are distance about 20 minutes one from the other. So what we can collect nowadays is what is called the very short arc of optical observation, alpha and delta. And typically this very short arc is not enough to compute an orbit. In this case, we speak about a 2 short arc, TSA in short. What we can compute in this case is an attributable, that is a vector consisting in the angles, alpha and delta, and their rates, their time derivatives, alpha dot and delta dot, at the mean epoch of the short arc. So to compute an orbit, what is missing is the radial distance and the radial velocity, rho and rho dot. So what we can do is to try to put together the information contained in 2 TSAs to have some hope to compute an orbit. And of course, this is challenging operation with the modern telescope, where the number of observations per night is very high, because what we can do is to take the 2 short arcs, 1 per night, and you have order of n power 2 pairs of 2 short arcs, that is attributables, that you can put together, and you have to apply a suitable linkage algorithm to these pairs. Of course, the alternative is to pick one observation for each 2 short arc, each night, and to apply Gauss method, for example. So you have to solve a polynomial equation of degree 8 n power 3 times. So in order to exploit the advantage of the 2 short arcs, you should have a linkage algorithm that is as efficient as Gauss method. If you are able to find such a linkage algorithm, so you can appreciate a big advantage in terms of computational complexity. So the first integrals of Kepler motion turns out to be a nice tool to perform this job. So these were used first by Tuff and Dole in 1977. They proposed to use angular momentum and energy conservation to write the equation for a linkage, but they didn't employ a polynomial formulation, which was possible to do. And we did this much later in 2010, and we got a polynomial at degree 48, which is quite far from the degree 8 of Gauss, for example. But 1 year later, we were able to decrease the degree to 20 using in place of the energy a suitable projection of the Laplace lens vector. And some years later, using a combination of all the first integrals of Kepler motion, we were able to decrease the degree to 9, which is close to the degree 8 of Gauss. So we are glad of that. And I am going to speak about this method. What the Keplerian integrals methods can do is to join 2 short arcs which are quite far apart, even after 1 revolution of the small body. Okay, so this is a big advantage with respect to classical methods of orbit determination, preliminary orbit determination. So let's give a look to these integrals. These are the conserved quantities, no? Angular momentum, energy, and Laplace lens vector. Bear in mind that our unknowns are the range and the range rate. So what we can notice is that the angular momentum is a polynomial quantity, vector quantity in these unknowns. The energy and Laplace lens vector, no, but only because of this red term, mu over square, the norm of the heliocentric vector position of the observed body. Okay. What we can do is to try to set down the conservation laws, all the Keplerian conservation laws, so angular momentum, Laplace lens vector, and energy. But there are those unknown terms that are not polynomial. So what we can do is to combine all these conservation laws in a way to produce this equation, which do not contain all the information contained here, but anyway allows us to extract a univariate polynomial equation degree 9. Okay, this polynomial equation has some optimality property that I have not much time to explain, but in a certain sense, we cannot do better than that. So since I have not much time, I show you some experiments using this method of degree 9. So we made some tests with some observations collected by the Posters 1 telescope, more than 800 main belt asteroids were considered here. We used the real data and also simulated data with different level of errors. I mean, no error here, then 0.1 arc-second error, 0.2 arc-second error. So of course, using the linkage method, you can find true linkage and false linkages. And we had a quantity just to measure the reliability of the solution. This quantity is called the chi4 here. So here we plotted the distributions of the chi4 norm, the log 10 chi4 norm, for the true linkages, the green ones, and the orange ones corresponds to a false linkage. So you can see that there are a separation between these two distributions. This allows us to use this chi4 in order to distinguish more or less within some threshold the solution. I also played with the PS Posters 1 data of some near asteroid. For example, here you have the asteroid Geographus, and I collected all the tracklets made by Pan-STARRS. Here there are 13 having at least 3 observations each. Here are the dates, so you can see that they go from 2011 to this year. And I tried to link with this algorithm every possible pair of tracklet. So in this plot, I colored one box if the linkage was successful. And you see that 2 different colors. So gray means the linkage was successful. Black means that in addition to be successful, the linkage, also the quality control with that parameter chi4 was successful. That is less than 1 was the value. So you can see that, for example, here we were able to link the tracklet number 2 with the tracklet number 11, and they are quite distant apart, some years. Okay, here is the plot of the difference of the orbital elements and the computer orbital elements and the real ones that we know. And you see the distribution with light color without quality control, and with black color having also the quality control of the K4. So I also had a similar picture for the asteroid Apophis. And to conclude, I can simply collect which are the most important sentences in this talk. That is, we can perform a linkage operation with the polynomial degree 9, and that using this conservation law, we can do this job for tracklets which are quite far apart. So in my opinion, this argument looks promising for the new generation surveys and the new kind of observation today. Thank you.
One quick question for you.
Was not the question.
I maybe have just a quick one. So one of the challenges with Rubin is that we're going to have about 1 million attributables per night. And then do you have any suggestion how to quickly cut out, like this grows as n squared, right? If we try to do pair to pair, like how to quickly remove large numbers of attributables.
You are right. The problem of filtering couples to be tried, tested with this algorithm, we already took this problem in consideration, and we have some preliminary filters that we apply in our test. I think on that side, the research could be pushed on because I think some more efficient fits could be produced, but we already have some. Yes.
All right. Thank you, Giovanni, again. So for the last 5 minutes, we'll just have, I just want to remind everyone that in addition to all the talks you've heard here, we also have a number of poster contributions, and poster in this case means actually a short talk. They've all been uploaded and they're all on YouTube. All the poster authors have submitted one slide for our flash or lightning talk presentation, which we're hoping to do right now. There's something going on over there. I hope that doesn't mean there are problems. Okay. And so that will happen in about a minute or two, and that will then conclude our session. But so please look at these short advertisements to what the talks are about, and then take a look at the talks at your own leisure on YouTube.
So for online, since all the speakers are online for this, you get 1 minute. The slides will be advanced by Mario. All of you are unmuted because that's the easiest way to do it. So if you're not talking, if you can just try to be quiet, just because you type or et cetera, we'll hear you from the other speakers. So hopefully this will be as painless as we can make it. All right.
Click on.
All right. Can you hear me?
All right.
Yes, 1 sec. They're just minimizing the screen so we can.
All right, Kathleen, you can begin.
Yeah, go for it.
All right, so I'm Kathleen Krieger. My talk is on the Atom Precovery service. We built this service with 2 motivations. The first being the need to extend the arcs of objects discovered with a different linking algorithm. And the second being that the traditional methods of doing precovery searches are too slow, especially as the volume of data increases, which is very relevant for this case. So we created a new algorithm which speeds up the method of doing precovery searches to the point where you can do a single object precovery search on all of NSC DR2 in about 35 seconds. We hope to add additional data sets, including eventually LSST. And you can check out the full talk either on the YouTube page, or you can also try out the service for yourself there at atom.b612.ai.
Excellent. Thank you. Switching doesn't work again. Yeah.
Bryce, you'll be up in 1 second. We're just getting the slide advanced.
All right, Bryce, you're next.
Go for it, Bryce.
Hello, can you hear me okay?
We can hear you.
Hi, my name is Bryce Bull, and I'm a postdoctoral fellow at NASA Goddard Space Flight Center. My short talk is about the discovery of the first known asteroid located entirely within the orbit of Venus, Illo-Chaxton. This asteroid was discovered by the ZTF Twilight Survey in January of 2020. The asteroid has a 10 million year lifetime, likely in state to have an impact with Venus. We find that there might be a factor of 10 discrepancy between the Inno model and what we actually find with the discovery of this asteroid, and which may hint that Inno models might have to be revised, such as including an additional source of asteroids in the inner solar system. There's a QR code to the paper which describes this discovery, and you can find the complete talk on YouTube.
Excellent. Thank you, Bryce. Moving on to Siegfried Eggl.
Yeah, hi everyone. My name is Siegfried Eggl. I'm currently faculty at the University of Illinois at Urbana-Champaign. And I have the pleasure of talking to you about the impact of mega constellations on solar system science with LSST. So as you know, private companies have started launching tens of thousands of satellites in low Earth orbit. And in spite of best efforts on both the operators and folks at the LSST, their satellites are still very bright. And so this has implications for static sources and cosmology, as was already laid out in previous work. What we try to do is we try to assess how those satellites would influence LSST's capability of discovering solar system objects. And we do this by trying to do a real forward modeling with actual Starlink satellite orbits. Of course, the whole constellation hasn't been launched, and this is very much work in progress. But long story short, we find that we're probably going to lose like on the order of a few % of detections of solar system objects due to satellite tracks. And that's not great, but it's also nothing to panic about. The only concern that we have at the moment is that since we need kind of 6 detections to claim a discovery, there is this lever arm that we should probably keep an eye on and see how that goes. I'll keep you posted. Thanks.
Thank you, Siegfried. And next talk.
Yeah. Hello. My name is Antonio Vanzanella. I am a master student in machine learning at Partenope University of Naples. In the poster, I present the work of my master's thesis, aimed at building a pipeline to detect solar system objects that move too slowly in the LSST image to be found with a standard technique. If you are interested in the application of neural networks to this problem, please come to YouTube and see my poster. You can also hear more about this project in the next session, where I will be giving a very short talk. Thank you.
Thank you. And our final talk is by Tom Wag.
Hi, my name is Tom Wag. I'm a PhD student at the University of Washington. What I've got here is the Hybrid Solar System Catalog. So we made this essentially because we want to make predictions that account for prior detections. Currently, we use a full solar system catalog for many things, and this means we could get into a situation where we're predicting the rediscovery of Ceres or some sort of large asteroid. So this is kind of trying to avoid that. And you can use this in exactly the same way as you'd use like an S3M, the simulated solar system catalog, and it has statistically indistinguishable distributions from the simulated catalog, as you can see from the plot on the right. You place plot the difference or lack thereof. And this is pretty fast as well. So we can do it pretty much every night. As we get more detections, we can then update it and keep the real things within the hybrid catalog. So yeah, the full talk link is there at the bottom, as is my email and a link to the code if you'd just like to try it yourself. Thanks.
Thanks, Tom. And let's thank all the speakers in the session and the poster speakers once again. All right, that concludes the session. Let's go get some coffee at the break. And thank you for sticking with us for so long. I think we'll learn about the technology every time we do these. Thanks.
Perfetto, grazie mille. Ok. I am surprised that Darko is not here. Because we still have to wait a couple of minutes, but he was here. I am really surprised. He's joining us. Sure. So the idea. Don't worry, you can bring the cakes. It's not strictly speaking is not allowed, but you know, I don't think that this is going very long session. So I don't know whether there is anyone connected on the Zoom. No one. Okay. So we received a request to organize this session on the very first day of the meeting in order to give the opportunity to the colleagues that were interested in organizing the next LSST meeting to talk with each other and see whether we can converge on the organization of the next meeting, because according to the rule that has been fixed during the previous editions, this was always announced, as I mentioned this morning, before the end of this meeting. So I know that there are colleagues interested, but I think that it's time that you are going to introduce yourself and see and say what you would like to do. Sorry?
I speak loudly enough, and there is no one on the Zoom, so no need for that. Okay, one things we used to organize these meetings every other year, and now we had a long gap. But we always had also an idea to have those LSST Europe meetings once a year when things start rolling. So idea is if, and we did talk to Croatian and Slovenian crowd a little bit, and in a way I suggested to them and anyone else who has any kind of opinion put ideas forward.
Okay, I have a point to mention. Originally, this meeting was thought to be alternative between Europe and Asia, because obviously they are also interested. Yes, they started, but the point is that the idea of the alternative years was also to give them the opportunity to organize their own meeting, because from the logistic point of view is not really nearby. So right now, to my knowledge, but in case there is anyone here that knows of any initiative from Asia, whatever is the definition of Asia, please show up and tell me whether this is we should discuss or take into account this opportunity as well. Right now, the Slovenian and Croatian colleagues have already manifested their interest, and there is no problem at all on my side. The only point that we should discuss is whether the meeting every year is exactly what we are looking for or not. Concerning this point, I have a suggestion, but a suggestion that is a consequence of being contributed to organize the meeting this year in Rome. I have the feeling that the cut of the meeting should be slimmer than the current one, because we really do not need to have one more PCW in Europe after the one that is organized every year in Tucson. So this is just a suggestion. Then you can decide to do what you think that is more appropriate for your community and for LSST. This is just a suggestion. Here, probably due to the gap that we have had for the COVID, the meeting was really big at the very end. So it's a pleasure, there is no doubt, but it's something that we can think about, in particular, if we are going to have a meeting every year. This is just my opinion, nothing else. So once again, please.
Thank you very much for the introduction. And in principle, I agree. Well, I should first introduce myself. My name is Lovro Palaversa. I'm from Croatia, from Zagreb, from Ruđer Bošković Institute, and I'm the leader of the Croatian in-kind contribution team. And here I'm representing the initiative from Slovenia and Croatia. We, in principle, have volunteered to organize the next LSST at Europe meeting. That would be LSST at Europe 5. So with me today here are Andrea Gombac from University of Nova Gorica in Slovenia, and Tomislav Jurkic from University of Rijeka. Concerning what has been said thus far, I agree in principle that with everything that was said, and in particular with the fact that the LSST at Europe meetings are somewhat shadowing or duplicating what's happening in the PCWs. And in that sense, I think it would be prudent to make them a bit more focused for the European crowd and European scientists, and not just to repeat everything that was happening at the PCW, especially since we can expect in the future that almost all the meetings will be hybrid in nature. So there is no point in repeating things that are being said like every 2 months and so on. Regarding our initiative, so we've made some preliminary inquiries regarding the possible venues for the meeting. And we think that the probably best location for us would be the western coast of Istra. That's in the northwestern part of actually northeastern part of the Adriatic Sea. Like I said, the meeting will be co-hosted by Croatia and Slovenia. And this region is particularly interesting because it's within driving distance of many institutes in Slovenia, well, of institutes in Slovenia, of institutes in Italy, Croatia, Hungary, Austria, Germany, Serbia, and Hungary, I said also, Austria, yes. So I think it would, sorry? Hungary, yes. So I think it would be easily reachable by many, and the others can fly into one of the 3 or 4 airports that are within an hour and a half of driving from the possible location of the meeting. I've made some inquiries with the possible locations where the meeting can take place, and we have in principle a choice of conference venues that can host from 200 from 100 to 1,000 people, and that depends on the future plans and what we decide if we choose to do this in Istra next year. So with respect to that, we would need to make some decisions on actually how to proceed with the form and the shape of the meeting. And I think this is pretty much all that I can say at this point. Thank you.
Thanks a lot. Okay. So thanks a lot for the introduction. I don't know whether there are suggestions or any kind of supplementary information, or whether there are other communities that are interested after. Do you have questions on? No, there is no one on the Zoom. So whether there are other communities that are interested or planning to be in line for LSST Europe 6, in case there is no change or no variation with Asia, this is something that, once again, we have time for sure, but yes, please.
I was thinking that despite, whatever our colleagues from Asia are gonna do, because the commissioning is gonna happen in, end of the next year, 2024, would be good to have a conference, no matter what, yeah.
Sorry. Yeah, thank you. So one of the ideas why we wanted to have this meeting is because we hope to have first images by then. So it would be a very nice thing to do to present them there.
Just because this was the same question that the previous one asked to us, I guess that you are pretty confident about the funds for the organization you have already somehow supported.
Of course, with the funds, it's difficult. I've had some success 3 years ago with the funding agency that funded the meeting that was similar to this, not fully, but there can be some external support. Of course, we can't guarantee anything. And in any case, we would be happy to receive any support that we can get from the LSST corporation. So that's encouraging.
Let's say clearly that we have been supported by LSST corporation. Any other suggestion or plan? Rob.
Thanks. Just to be clear, we're talking about a year from now, or so next fall or next northern fall? Okay. Yeah, good. Thank you.
Correct me if I am wrong. I guess that in 1 year, also the process of the in-kind is going to be on a more solid path. May I say that?
I think I'll say a few words about this tomorrow in the plenary too, but yeah, we hope to have the current program of the programs that we're dealing with pretty much wrapped up and with data rights agreements done by then. I hope to make actually real good progress in the next few months toward that end. So yeah, that should be much more advanced at that point.
Yes. Okay. So
I wanted just to add that to make to put the action going forward, that we would need the number of the participants, the expected number of participants, and probably the format of the conference. Will it? Are we going to stick with the same format we do it this year? So with 5 days and 2 or 3 parallel sessions, and also to, I don't know, to see how many participants we can expect. Will it be 150 or I don't know, 300 maybe?
The problem is not the number, just because the experience is fresh. The problem at the very end was not the number. The problem was the many different rules for registration. Till a few days ago, we didn't know exactly what was going to be the number of participants, because we have had really a mixed bag of participants with 1 day, 2 days, 5 days, only on the web, in presence and on the web. And this is not easy to handle. Well, it is easy if you have $50,000 or euros in such a way that you can cope with all the expenses and then you recover later on. But when you have to wait to have the money in the account to do everything, is not easy. So my suggestion, once again, probably you should try to find an easier way to organize the things. Once again, my opinion, in case you find a different solution, I am very happy for you. But this is just the difficulties that we have had.
I would leave the format and content of the conference to the future scientific organizing committee. They are those who are going to do the thing. And basically, yes, probably is going to be a 5-day conference, similar, but kind of number of parallel sessions, etc. It is up to the both SOC as well as what you can find with the rooms and in the venue.
Well, I didn't want to introduce this before we actually agreed on the meeting happening next year, but the major problem for us is we certainly have enough options in terms of the places where we would like to organize this, but we need first to know at least the approximate number of people that we would be expecting. Because the problem might be that unless we book a venue sufficiently early, we might lose it. So this would significantly reduce our choices in the future. So I think that I would be very happy if by the end of the meeting we say like, okay, we are expecting 300 people. We are looking for a venue for 300 people, full stop. I understand that things might change in future, but we have to make a decision.
Yeah, but the problem is that no one in this room can tell you what is going to be the number. And this was the same with us, because we started with a meeting in which the number of people in presence could not be higher than 90. And then fortunately, the boundary conditions changed and we increased the number. But hopefully this is not going to be a problem for the future, but the number of people that are going to register, this is something that it is unknown at the very beginning. The only thing that we received a very strong request was the requirement to have at least 3 rooms for the parallel sessions. So this is not a matter of discussion. So all the other stuff is unfortunately affected by uncertainty.
Yeah, I mean, I was thinking that maybe the next year, if we are really close to the first light, that there will be maybe more breakout sessions. I don't know, like on Link workshop, they had like 4 or 5 breakout sessions at the same time. I don't know. I mean, if the people decide to do it to go forward with this format. Yeah. And then the other thing is that if you book a hotel with the venue, with the conference room and everything, usually they require to pay in advance 10% or whatever, just to confirm the booking. So that means that in the next 1 month, probably we would need to book the venue and to pay something in advance.
So I think that we are in a very good condition because we already have a proposal for the next one. We are not in a hurry. You have 3-4 days. The only thing that I am going to ask you is just to have 1 or 2 slides, and one of you is going to show just before, on Friday, just before the end of the works, in such a way that we can say that this is the plan for the next one, is the next year, the location, and what you consider what is interesting to mention early in advance. Is this okay? Any other suggestion or Darko?
Just thinking, okay, you can delay it till Friday, but also it could be interesting to announce it during the conference dinner.
Absolutely. You know, in particular, after a couple of grappa, you can do. It was a joke. It was a joke. But it's clear that we can start a pour parler during the social dinner, and then it's going to become official on Friday, just before the end of the meeting. Okay? Sure.
Thank you. And just the curiosity, do you know what was the percentage of participants which registered just for 2-3 days?
I do not have the exact number, but let me rephrase slightly in a different way. The number of participants registered for 5 days is a minority. All the others are going to be present for 2, 3, 1 days, but the ones for which they are going to stay for 5 days are really a minority. How much? Right now, I do not have the number, but I can tell you tomorrow morning. Yeah, the bulk is splitting the stay. You know, end of October is, including me, is busy teaching time, so it's not easy to stay for 5 days away. Yes, we have been forced for this date because originally we were thinking between end of September and beginning of October, but it was not possible because there was no room available here. And so the only window that we have had was the last week of October. So unfortunately, this was tightly connected with the location. With money, we could have other places, but we didn't. So this was the reason why we ended up with a date that was a bit late for the academics. Anything else? Okay, great. Thank you very much for your attending this session.
Non ne sono sicuro. No, quello è qualche problema. No. Sì, c'è un problema.